All right, let's get started. Welcome to AIMI Grand Rounds. This is the first in a monthly series hosted by the Stanford Center for Artificial Intelligence in Medicine and Imaging, or the AIMI Center. These sessions will be held the fourth Tuesday of every month to feature AI research being conducted in our clinical departments and to raise awareness of AI capabilities among clinicians. We will be exploring cutting-edge AI research and its clinical applications in healthcare, featuring interdisciplinary lectures from experts in medicine, engineering, and many other fields. We intend these sessions to bring together our community of clinicians and scientists who are creating new methods for the development of AI and evaluation and deployment of machine learning systems. A couple of housekeeping announcements before we get started. To claim CME credit for this session, please text the code provided to the number listed in the chat. You'll also receive instructions via email after the session. And if you have any questions during the talk, please submit them using the Q&A function, and I'll address them at the end of the presentation. A full schedule for future Grand Round sessions will be posted on the AIMI website, and you can also find that link in the chat. And then lastly, just an announcement about our fantastic summer programs. We have a summer research internship and health AI bootcamp for high school students. These are virtual programs designed for high school students excited about the intersection of AI and healthcare, and it gives them an opportunity to learn and grow in the field with hands-on research and lectures by experts. The applications are open and the deadline is February 28th, so if someone you know might be interested, you can find more information on our website, which is linked in the chat. And please feel free to pass along this information to any high school student you know who might be interested. All right, with that, let's get started. So what I'd like to do today is to focus on AI in radiology, and in particular, the research that I'm doing in my own lab. We'll be able to hear from, I'm sure, others in radiology as we move through the schedule of AIMI Grand Rounds. And I always like to start with a clinical case. So this is a case of a 83-year-old woman who's had her aortic valve replaced, occasionally gets short of breath, came in about 18 months ago for this chest x-ray, which was read as normal, and then recently came back, and you can see she now has a large mass in her right chest. And if you look back at the prior study, you can see that there actually was a small mass, partially behind a rib, in among the hilar vessels that ended up being a cancer in this case. And the reason I show this case is that 3 to 4% of diagnostic imaging interpretations contain clinically significant errors. We know this from the literature. And this is true not just of radiology, but cardiology, pathology, others. And so we need help as radiologists, and these tools are really, one of the use cases is designed to help us with exactly these kinds of cases. So we all in the research lab feel a special obligation to bring these technologies to our patients. These are my disclosures. I'm involved with several startups. I do some consulting, and our center and the school receives support from various corporate sponsors through our affiliates programs and other grants and contracts. All right, so outline for today is I want to give everyone some background. Just take 5 or 10 minutes to talk about how we got here, why are we so excited about AI in medical imaging in particular, in radiology, and then give you a sense of what's happening in the lab with respect to image analysis, the themes that we're seeing, and how that's going to affect the clinical care and how these algorithms affect clinical care. Then we'll talk about foundation models, ChatGPT, large language models. Those are very interesting and how they'll affect clinical care in radiology. And then spend a fair amount of time at the end talking about the challenges. So this all got started long ago, long time ago, 1958. This was one of the earliest neural networks called a perceptron. And you can see inputs on the left. We have some math going on, some weighted sums internally, and then you get a numeric output when you can threshold it for a yes-no decision. So that's the earliest neural network. I'm not quite that old, but I can tell you that my undergraduate thesis here at Stanford in 1981 was on neural networks. And I concluded that they didn't work. And in fact, I was not alone at that time. And really the reasons for that are that we didn't have the data set size that we needed to really train one of these well. And we didn't have the computational power to do that. And in fact, the computer scientists have figured out how to update the parameters on these models to make them work very well as well. The other thing that really happened that catalyzed the early progress in this area is something called ImageNet, which is a database that was put together by our own Fei-Fei Li, who's on the faculty in computer science here and leads our Human-Centered AI Institute. This is a database of 14 million images. There are 21,000 different types of things in this database, 800 types of bird, 900 types of tree, 150 musical instruments. And you can see on the left, this is an example of the garden spider. And the images are in different orientations. They have different backgrounds. So it was a nice, challenging visual recognition task. And so every year, the computer scientists would hold a challenge to see whose algorithm was the best at recognizing these objects in this database. So what I'm going to show you now is the error rates of the winners of that competition each year. So in 2010, 2011, we had over 25% error rates. In 2012 was the first time these neural nets were used by Jeff Hinton's lab at the University of Toronto. And then the next year, the winner was Yann LeCun, who was at NYU. And everyone was using it that year, and the error rates dropped further. And then it was won by a team from Google, then from Microsoft, and then teams from Singapore and China. And you can see the error rates are dropping dramatically. And at that point, one of Fei-Fei's postdocs said, I wonder what would happen if a human took this? How well can humans do on this? And so he learned all the dogs and cats and trees and spiders and things and took the test and found his error rate was about 5%. So we're getting near human level performance from this from these systems. And in fact, you can see the error rates are flattening out. So they thought, we're really extracting almost all the information we can from these images. We need a more difficult task. And so they settled on something called automated captioning. This is a breakfast table, a photo of a breakfast table, and all of the bounding boxes here and the text were created by AI. So bottle of water, cup of coffee, plate of fruit. And Fei-Fei showed this slide at the 50th anniversary celebration of the computer science department here at Stanford. I happened to be there. It was at Arriaga Center on campus. And I know when I saw this, I thought, hey, that's what I do as a radiologist. I look at pictures, I find things, and I describe them in text. And I think everyone else had that same insight. And so we all realized this was an incredible technology that was going to have a profound impact on the practice of radiology and medical imaging. What's happening under the hood? Well, this is machine learning. So we are the algorithm or the system is learning from examples. So we have here an example of a malignancy on a mammogram, a benign mass on a mammogram. We feed all those examples to the neural network. And I like this schematic because it's all these Greek letters. It just shows you it's just math going on in there, a bunch of equations. And then based on whether the answer, the algorithm gets the answer right or wrong, the computer scientists have figured out through something called backpropagation and gradient descent how to update the parameters a little bit each time to make it more likely that it'll get the answer right the next time. So over many, many billions and billions of iterations of training, these systems get to have excellent performance. So more under the hood, more detail. So with respect to images, if we're doing image classification, is it benign or malignant? Images are just matrices of pixel values, which are just numbers. And the neural network takes those numbers and does some matrix math and turns them into a vector. Okay, it's a list of numbers. This is a slight oversimplification, but I think you'll bear with me here. So a feature vector. So this represents the essential diagnostically important features from that image. This isn't strictly true, but I like to think of it this way, is that perhaps one of these numbers might represent the amount of spiculation, or whether there are microcalcifications, or whether it has a lobulated border. Again, the machine makes its own set of features that work best, but that's a good way conceptually for us to think about it. This is a vector of features, and then we can do a regression on this vector. So we put a coefficient in front of each of these numbers, and we get one number out the other side, we threshold that, and then based on whether it's above or below the threshold, we classify this image as benign or malignant. And that's what's happening. It's a bunch of math happening under the hood. That works very well for classification. We'll talk about generation later. And as a result of this, we have an industry. So this is the plot of all of the FDA-cleared machine learning algorithms over time, and you can see it's grown dramatically. This is partial data from 2023. And if you look at where are these algorithms targeting, well, more than 3/4 of them are targeting radiology. And in fact, this has been true and continues to be true. The most recent update, there were more than 1,000 algorithms now cleared. Again, still more than 3/4 radiology, more than 85% imaging when you add in cardiac and dermatology and all the others. Just to illustrate, these are the logos of the over 100 companies that exhibited at a recent radiology professional meeting. All these companies are selling algorithms to radiologists. So this is a real industry today and something we have to contend with. Why is it that radiology is out front with all of this? Number one, I think our imaging data is plentiful. Our hospital here has over 1.6 petabytes of medical imaging data. We have over 3 petabytes of pathology data, 1.6 of radiology data. These neural networks are just very good at processing images. And I think our data is maybe a little more objective. So when you take a radiation, whether it's ultrasound or radio frequency for MR or X-rays, and you send it at some tissue and you get either projection or reflection of imaging energy back, you get some very good three-dimensional information about what's happening at a particular spot in the body, which is fairly objective, I think, relative to maybe what a patient might describe a symptom. It gets written in the chart. We need to use natural language processing to understand what that is. So I think those are the reasons why radiology may be leading. So that's kind of the background. That's why everyone in radiology is very excited about AI right now. So now I'd like to talk about some of the things happening in the lab. And I want to just thank all of my lab members. I'll be focusing mostly on the work in my own lab, except for a couple of examples early on, just to give you a sense of the breadth from some other labs in radiology. So you'll have a chance to hear more, I think, about what's happening in other radiology labs in this speaker series. The other thing I'll mention is I show some faces of who did what work, but everything's a team effort in the lab. So this is really all a group effort. All right. So this is, I like to call this the imaging life cycle, and AI can really have an impact across the imaging life cycle. So even test selection, you can imagine AI examining the chart, machine learning, looking at the chart and predicting positivity rate among similar patients, predicting whether that test will be positive. I'll show you in a minute algorithms that can help to lower radiation dose, lower imaging times, lower contrast dose just by using some of these neural network methods to enhance image quality and resolution. Quality control. So you have patients who are on the scanner, the technologist is looking at the image, they may be moving, the patient may be moving or breathing, and technologist might not notice that until then the radiologist looks at it a couple of hours later. Now you've got the patient on their way home, they've excreted the contrast, they have to be called back. So we can reduce that by helping the technologist recognize problems with images at the console. So if I'm on call on a weekend, I might come in, there are 100 cases waiting for me from predominantly the ICUs. I would love to know which of those, what 10 cases are likely to have positive findings that I can read them first and get the feedback to the ICU so they can address that problem and decrease the length of stay. Computer-aided detection, so that's the kind of thing that would help us with that case I showed you, the nodule that was missed on the chest X-ray. Classification, so you may have a radiologist out of his or her comfort zone, or maybe a non-radiologist in an ED in a rural area reading an X-ray and see something in the bones on a chest X-ray. Could we help them with a differential diagnosis using machine learning? Absolutely. And then reporting and communication. So how do we make sure that the right information gets to the right place at the right time? And the natural language processing can help with that. All right, couple of examples from this cycle. This is the work of Greg Zaharchuk's lab, one of our neuroradiologists, used with permission, a pre-contrast MR. And then sometimes for our perfusion studies, we give a 10% test dose just to look at the contrast circulation times. And so the idea is, could you predict what the full contrast would look like from the 10% contrast? And sure enough, you can. And so this is a synthetic image, and you can see the actual 100% contrast dose right next to it, and they look very similar. And this publication here at the bottom showed that, in fact, you can make the same diagnoses as well. And so there's really nice work to show not only can you reduce contrast dose, similar kinds of methods can reduce imaging time in MR, can reduce radiation dose in PET, and the like. And so you can get these inexpensive devices. Ultrasound devices, we all know about point-of-care ultrasound, portable MR machines that you can wheel around the hospital. These are devices that we might not think of, except if we have these kinds of machine learning methods to kind of make the images of a quality that we would consider diagnostic, which might not have been possible years ago. Another really impactful work. This is from Bao Do at the VA, one of our radiologists at the Palo Alto VA hospital. He's developed AI algorithms that can detect all of the abnormalities that you would see on a musculoskeletal X-ray. So arthritis in the right hip, prosthesis in the left hip, and then the algorithm pre-fills a template. And so you get a draft report. So this is much like working with a resident where the images are previewed and the report is drafted. And so this is a potential for time savings and also improving the consistency and quality of reports for patients. And this has now been used on tens of thousands of patients across the VA. Very nice work. Next, I'd like to just feature an algorithm that we have in a clinical trial. This was originally developed, led by Matt Lundgren when he was here, and I inherited this work when he left. This algorithm, it's a pneumonia detection algorithm in a prospective clinical trial across many of the EDs in the Intermountain system. And they had an algorithm which used age, chief complaint, vital signs, nursing assessment, lab values, chest X-ray findings to determine, this is for patients who come into the ED who may have pneumonia, to decide whether the patient should be on antibiotics. And the thing that was the last item to come back was this chest X-ray findings, because they waited for the radiologist to interpret it. Then they did natural language processing on the report to determine whether it was pneumonia or not. And they thought with Matt, hey, why don't we just have the algorithm look at the pixels and decide immediately? And so as that algorithm has been implemented, you can see this is the overall algorithm. These are the results. It has resulted in a 38% reduction in all-cause mortality, decreased time to antibiotics by 10 minutes, antibiotic prescribing more concordant with guidelines. More patients were able to be discharged as outpatients without any change in the 7-day readmission rate. So really nice results from this kind of integrated pneumonia algorithm incorporating imaging AI. So those are just some examples of the kinds of things that are coming out of the research lab in terms of image classification. And now I'd like to move on to foundation models and large language models and ChatGPT and how those are likely to affect the practice of radiology. So what is a foundation model? This is a term coined by Percy Liang's group in our computer science department here at Stanford. And what it really means is that you take a very large amount of data. It might be the entire internet in the sense of ChatGPT. It might be a large amount of medical images. And then we train using what's called self-supervision, and I'll show you what that is in a minute. That's kind of the innovation. And you develop a model that knows a lot about something, whether it's medical images, whether it's text, and can be used as a foundation for other tasks. So we can adapt it to question answering in the case of ChatGPT, or perhaps image captioning or object recognition in the case of medical imaging. So a very powerful concept. All right, so let's talk about self-supervision. The way this works for something like ChatGPT is that the computer essentially plays a game with itself. So it hides words, in this case, in this text passage. This is medical text. So shortness of breath, low grade fever, elementary school teacher, she appears anxious. So it hides that word, and then it attempts to predict the missing word, and does this again over and over again. And based on whether it gets the answer right or wrong, it updates its parameters to make it more likely it'll get it right the next time. And again, over playing this game with itself over billions and billions of iterations, it gets very good at predicting the next word or generating the next word. So these are generative AI algorithms. In radiology, we have an even better advantage with respect to this self-supervision. So we can do something called contrastive learning. We are fortunate to have not just the image, but we have an expert text description of what's happening in every image that we have in our database. And so we can build, so this is a neural network that encodes information from images here. And this is what's called a transformer, a kind of neural network that encodes information from text. And then we can build a third network that tries to decide whether the text matches the images. So then we feed it, like in other words, is that the report that described what happened on that image? And then we feed it matched and mismatched pairs. And we do that again over and over again. It's a game the computer plays. And all three of these neural nets get very good at what they do. So that's the training process. Now let's say what happens when you have a new image. All right, so here's our new image. We take that neural network that we've trained to encode information from images. We encode the information from the new image. Then we create some artificial prompts. So a positive prompt saying, pneumonia is present, a negative prompt saying there's no evidence of pneumonia. And we encode both of those using the network that we've trained to encode information from text. And then we use that third network to score, is this a match or is it not a match? And that score, the prompt that scores the highest is used to classify the image. So here the negative prompt got the higher score. Therefore, we say this chest X-ray is negative for pneumonia. And so what we've just done is we've built an image classifier using only the data that's present in the medical record, this paired data of text and images. We haven't needed, except to evaluate this, we haven't needed any expert labels. So those labels are very expensive to produce. And this just gives you a sense of the results. So this is comparing on several, atelectasis, cardiomegaly, consolidation, different conditions. And you can see the green dots are the accuracy of the humans and blue dot is the AI. So we're getting human level performance from an algorithm trained in that way. So that's pretty powerful. Now, what are the challenges of training these kinds of models and language models in particular? One, we have the inherent limitations of the training data. So if Taylor Swift gets a neuropathy, all of a sudden there's a lot of talk about neuropathy on the web. And if we train on the internet data, that's going to rise in our differential perhaps more than it should. There are issues you've probably heard of hallucination or confabulation, of making stuff up basically, because these are probabilistic systems. They're just predicting the next word, and they're going to try to predict the 51% word over the 49% word, and that's not always correct. And these are very good at language, but they're not good at structured tasks like planning and mathematics and the like. So the things that we're working on in the lab is something called retrieval augmented generation. I'm not going to say much about that today, but it's essentially combining the language skills of a neural net with the kind of a source that we trust. So a database or a website that we trust, and then or a patient medical record for that matter, and having a dialogue about that. And something I will talk about now is evaluation. So we spent a lot of time thinking about how do we know these systems are doing well or getting better? And so this is the work of Sophie Ostmeyer, done jointly with Akshay Chowdhury's lab. And she developed a training set of 20,000 chest X-rays and, 20,000 reports and from publicly available sources, and then used a variety of methods to perturb those reports to create discrepancies or errors in those reports, and then used a training procedure that was training against a group of reports, of ratings that were generated at Harvard by Pranav Rajprakash, who used to be a student here. 200 pairs of reports and human ratings, 6 different error types on these reports. And so she used that as a way of training, of finding how can we train a model that will mimic the ratings of radiologists as to the quality of these reports and the number of errors they contain, and use some clustering methods to cluster the different error types. And so here you see, the first was trained using GPT-4 and then using a less expensive open source model. But you can see the different categories of, false report of a finding in the candidate, or a missing finding, or misidentification, or misassessment of severity. And all of these develop a kind of summative score of the report. And you use some clustering methods to find these examples of each error type. So it's a really nice way to evaluate these. And this gives us a way of deciding, hey, is this new method that we're using better than the old method? And this has now become quite popular in the research community. Okay, so how are these models likely to affect the practice of medicine and radiology? I like to think about these 3 different ways. So first, small language models fit for purpose. So we can build a language model explicitly to summarize a radiology report, for example. And if we build that in the lab, that's going to have likely even higher accuracy than a model than a language model. Like if we can ask ChatGPT, hey, summarize this radiology report, and it will do that. But it won't be quite as good typically as something that we train specifically for that purpose. You'll see examples of that in a minute. But that is going to democratize that process. So it used to be, you have to be like Stanford and have a research lab to build those fit-for-purpose models. Now you can get very good performance right out of the box for very little cost. And so lots of places will be able to do these kinds of things. And then lastly, something that I think we'll see is that we haven't yet seen foundation models of the size in medicine that we're seeing outside of medicine. And I think when we do that, when we start to see these large foundation models in medicine, we'll have a kind of ChatGPT moment, that moment back in November 2022, when everyone said, wow, this is amazing what these models can do. And I think that we'll see that kind of jump up in performance, and we'll be surprised by what happens at that moment. Okay, some things that we've done in the lab to kind of enable some other uses of language models is something called RadGraph. So RadGraph is a technology. This was the work of Pranav Rajprakash when he was a computer science PhD student here at Stanford. He's now on the faculty at Harvard, but he and a team developed this ability to extract entities, concepts, and relationships from radiology text based on an information model that I developed for a book I wrote several years ago. And it essentially gives you a knowledge graph or a knowledge map of the report. So there's an opacity suggestive of infection, it's in the right lower lobe, etc. So this turns out to be very useful, and we've since, through the leadership of J.B. Delbruck, who's a postdoc and now was a postdoc and now is a research scientist in my lab, we've shown how this can generalize not just from chest X-rays, but across other body regions, other imaging modalities. And here you see just the heterogeneity of the size of reports across different modalities. And here you see on the right the accuracy of our entity relation extraction in the red versus GPT-4. So you get a sense there of the fact that out of the box, these language models aren't good at medical tasks as well as something that's built for that purpose. So just want to describe kind of how we can use this RadGraph technology with a language model like GPT-4 out of the box to help with some other problems in radiology. And one of those is that you're probably aware of the 21st Century Cures Act, which gives patients immediate access to their digital health information. And I can tell you from my own family that when we get our radiology reports, I get a lot of questions like, what is a mild intrasubstance degeneration in the posterior horn of the medial meniscus? And is it serious? And so what we do is we take a report like this, we use that RadGraph technology I just showed you to extract the concepts and hyperlink them. And when the patient clicks on a hyperlink, we then send that concept to a language model, and with some prompt engineering, we tell the language model to explain it. And we get these very nice explanations at an 8th grade level. The medial meniscus is like a cushion that helps your knee move smoothly. Over time, it can get a little bit worn. It's kind of like when your favorite pillow gets a little flat, but still works fine. So very nice explanations. And so you may say, well, that's great, but what about the confabulation, hallucination? Is there any, potential worry there? And so we did an evaluation of hundreds of these explanations. Myself and 4 residents, we all rated all these explanations on a 5-point scale. And what you're seeing here is the lowest rating by any rater of any report. So there were 2 reports that got rated as possibly harmful, and I'll show you those now. One is that the ipsilateral frontal lateral ventricle was considered part of the brain. That was considered potentially harmful. And the other is that the right mainstem bronchus was identified as a place where you can put an endotracheal tube to help you breathe. Well, that's really not where you'd want the endotracheal tube. So those were thought to be potentially harmful, but overall, these explanations are helpful with understanding and not harmful. And so we were encouraged by that and are planning a further clinical trial of this algorithm. Now, so far, we've been talking about generative models that take a language as a prompt and generate language as a response. There also, as I'm sure you know, are AI algorithms that start with language as a prompt and generate images or even videos. But here are some images: portrait of a kangaroo with the sunglasses in the style of Rembrandt, hamburger in the shape of a Rubik's Cube, 2 astronauts exploring the dark interior of a spacecraft. So these are all synthetic images generated by AI. And some students, and this is also work done jointly with Akshay Chowdhury's lab, some students asked, hey, I wonder what would happen if you asked this system or a similar one that was open source to generate a chest X-ray. And this is what you get. So something that's not particularly evocative of a chest X-ray, but sort of gives you some of the anatomy. And we thought, can you do better? So we took this open source model and we retrained the diffusion model, which creates the images, on a large number of chest x-rays. We retrained the language understanding portion and the bridge to it that understands the prompts. And we came up with this system that now can show me a right-sided pleural effusion. It will create a relatively realistic effusion, large left effusion, and so on. So we can then use this data to supplement real data that actually does improve the generalizability and accuracy of some of these models. So very interesting kind of data augmentation method using these sorts of generative models out of the box. Okay, so I've talked about the fit-for-purpose models. We talked about using the ChatGPTs out of the box. Now I want to talk for a minute about building our own medical foundation models. So I'll illustrate that with this plot, which is slightly out of date, but I think still illustrative. The size of the training data used to train the largest text or language model, inside medicine in the purple, outside medicine in the blue. 82 billion tokens versus 15 trillion. This is a log scale, so 100x difference. And the same is true for images. Much smaller training data sets in medicine versus outside of medicine. But even just using the data we have here at Stanford, we can substantially close that gap. And so that's something that we're working on, is to try to build a foundation model using all the 1.6 petabytes of data in our radiology PACS system and the reports as well. Just to give you a sense of how that might work, we've done some preliminary work. This is the work of Zhihong Chen, who's a postdoc in my lab, built something called Checks Agent, which is a model that was trained on 6 million chest x-rays and text reports. You can see here all the different data sources that Zhihong found to pull these publicly available chest x-rays. And when you do that, you find that the accuracy of a system trained in that way, using these methods, is better than previously published alternatives. So ours is in the red. This is accuracy on the y-axis. And you can see that these training methods on large amounts of data really do lead to higher accuracy. And others have replicated this kind of approach as well. Just to give you another, so we tested this on view classification, disease classification, question answering, text reasoning, image text reasoning, and so forth. The other thing that we did was a sort of a clinical study, and this was done also with Maya Varma, where we looked at the time that it took, so that it took a resident to write a report from scratch versus using the draft that was generated by the system. You can see there's a slight difference there, significant. And then here we have time that the attendings took to edit these resident drafts. There was no significant difference there. Then we asked just a subjective rating question on a -10 to +10 scale. Does the report answer the indication appropriately? The residents rating the AI rated about 5. The attendings rating the AI rated just below 5. And the attendings rating the residents were just above 5. So all, very similar kinds of ratings. And so really a nice experiment that showed the potential clinical value of something like this. Okay, so that takes us through kind of the early work on foundation models. Now I'd like to spend the rest of the time talking about challenges. And I love this framework for thinking about sources of bias and challenge in AI research. It was published in our annual review of biomedical data science, which is edited by our own Russ Altman. And this framework we'll use to discuss each of these issues. So let's start with problem selection and data collection. So problem selection is about having the right people in the room who understand the problem and make sure that you're solving a problem that's important and you're going to get the right answer for all the different groups that matter. Data collection. Let's talk about data for a minute. So health data is different, and health imaging data in particular is different. So we talked about ImageNet earlier. The size of the images in ImageNet are 224 by 224. If I asked a system that could generate images, show me a hippo in a lily pond in the style of Van Gogh, it would generate an image like this, which is 1024 by 1024, which is about the size of an abdomen CT. But of course, a CT slice is just one slice out of maybe 100 slices, and that's just the pre-contrast images. Then we have the dynamic contrast images, the post-contrast images. We have to compare to prior. We have to relate it to the EHR data, to the genomics data, to the wearable data, and so on. And so health data is complex, and these are not questions that get studied so much outside of medicine, and so it raises a lot of really interesting research questions that we enjoy addressing, the 2D, 3D, 4D questions, and the multimodal questions. The other thing that we need to think about with medical data is, of course, issues of privacy and security, and so we've spent a lot of time using these neural network methods to better de-identify medical images and medical text in particular. So this is the work of Pierre Chambon, who's an ICME master's student here, developed this method which takes medical text and identifies the PHI, the patient identifiers, using neural network methods, and then uses a rule-based method to replace them with synthetic data. So it kind of hides, if anything is missed, it's hidden in there because there's all kinds of synthetic PHI as well. So this is a highly effective state-of-the-art de-identifier. It's been available on Hugging Face open source for some time now. It's had over 10 million API calls since it was released about a year and a half ago, and can be used directly by developers in a browser, in an API, or using Python. Just to give you a sense of how accurate this is relative to others, we tested it on the left here versus all the other published algorithms we can get the hands on, ours in red versus the others, and these are on different accuracy on different data types, patient name, phone number, and so on. And then on the right versus the cloud algorithms. So this is versus algorithms available from Google, Amazon, and Microsoft. And you can see they're kind of okay with some things, phone numbers and dates, but really not very good with some of these other PHI elements. So this is an important and accurate step that we take when we want to make this kind of data available for research and also publicly available to others. So we have now in the AIMI Center an open data program that's released over 20 AI-ready data sets. And we use those electronic de-identification methods, and then we have human review of every image or every report to make sure that there is no PHI on those images. And then we make them available. The largest data set we made available is called CheckSpert, which is, or CheckSpert Plus now, because we started with just images. Now we have images, we have DICOM images, we have the reports, we have demographic data, so we can do research on bias and fairness. And that's been a very, very popular program. But if you think about it, it's really not enough, because Stanford is just one place with one set of demographic characteristics. We took a look, and this was in 2020, led by Amit Kaushal, who's a junior faculty member here, who looked at where is the training data coming from that's being used to train machine learning algorithms. It turns out that most of it is coming from just 3 states. And so we're not necessarily getting an answer for everybody across the country when we do that. One answer to that, and this was published in JAMA in 2020, one answer to that is another project that I'm fortunate to be one of the national PIs of, called the Medical Imaging and Data Resource Center. This was funded by federal COVID money to develop a database of images of patients who have COVID and who don't, for the development of AI algorithms. And we took a very intentional strategy of getting data from a wide variety of sources. And as a result of that, you can see that the demographic mix, and this is true across many variables, matches what you would see in the census. And so that's one of the ways that you can develop a diverse data set that's likely to get the right answer. If you train an AI algorithm, the algorithm will get the right answer for all the different groups. Okay, next, let's talk about outcome definition. This is like, what are you training against? What are you asking the algorithm to do? And to illustrate this, I'll use some really fantastic work that was led by David Larson here in radiology. It's the first algorithm we ever produced out of the lab. I think it's the first algorithm, machine learning algorithm that was neural network algorithm that was ever published in our radiology journal. The clinical application is bone age. So you take an X-ray of the child's hand, a child who's suspected of having developmental delay. And what we do is we compare it to the images in this atlas called Grulich and Pyle, which is incidentally published by Stanford University Press, and it's the largest grossing book in the history of Stanford University Press, because I guess every radiologist needs to buy it. And so we compare those images, and if the age matches what's in the atlas, we say, yes, the bone age here is 7.5 years or whatever it is. I thought this was a great application for machine learning. And you can see here, these are the results. So this is the distance from the right answer. So we had a panel create the right answer. So lower bars are better. And you can see that the AI algorithm in the light red was as good as 2 humans, was a little better than 2 other humans. So essentially, we're getting human level performance out of this AI. We looked at the heat maps, which sometimes can tell us a little bit about what the AI algorithm is paying attention to. We like that it's looking at the joints in the wrist, and that makes a lot of sense. And then, as we often do, we conducted a clinical trial of this algorithm led by Safwan Halabi. And we involved 1,900 studies interpreted by over 90 radiologists from 6 different centers. And what we showed was, again, where left is better and orange is the AI assisted, that the algorithm in general is helping. Okay, so it's helping radiologists do better when they use this algorithm. You say, that sounds like a wonderful story, and it is. It's a great story of success of AI. But I think one other issue that we should consider is that there are definitely differences in bone growth across different racial groups. And so this atlas, Grulich and Pyle, was developed from 300 white children who grew up in Cleveland in the 1950s. So we're probably not training against the right objective, and we probably don't have necessarily the right training data. So I think if we did this today, we might think about it, again, fantastic work, but we might think about doing it a little bit differently. Next, let's talk about algorithm development. There's a lot going on here. I'll just give you one example. This is something we think about in the lab all the time. It's how can we obviously develop better algorithms? But one of the nice methods that we've developed, this is from Maya Varma, who's a computer science PhD student in my lab, who's developed a method to look at mitigating spurious correlations. You could call them confounders, perhaps. But so here's just an example of this phenomenon. So you may have a bunch of images, and most of the images of butterflies show them on flowers, and most of the images of birds show them on branches. And so what happens then is that if you have a butterfly on a branch or a bird on a flower, the algorithm doesn't do quite as well. And this is, these are algorithms trained in this same kind of contrastive learning method that I showed you earlier with a text encoder and a vision encoder. So Maya developed a method where you can discover these learned spurious correlations between image features and text attributes, and then develop a learning method that prevents the algorithm from learning these spurious correlations. And so when you do that, it's called Ravel. You can see this is on real world data, this algorithm that she's developed versus other algorithms that have been developed to do the same thing. And you can see the accuracy here is much higher than the alternatives in both situations. So very nice work. Again, work on refining our methods to make these algorithms even better. Lastly, just talk about post-deployment considerations. So an algorithm that works on day one is great, but with shifts in the data that's fed to the algorithm, the performance can degrade. So we may have a new device that comes online, or even a new software version on the same device we found could affect the accuracy of these algorithms, or a new clinic that opens up with a different patient mix, or a new disease like COVID. So that pneumonia algorithm I talked about earlier that we were using in a clinical trial at Intermountain, when COVID came, we had to completely retrain it because it no longer worked because pneumonia suddenly looked very different. And the FDA actually has acknowledged this. They've given guidance now on something called a predetermined change control plan, which acknowledges that with these algorithms, you may need to refine them to local circumstance or change them based on the data that's being fed to them. And as long as you do so according to the plan that the FDA has approved, it's something new, right? Normally, FDA just approves a fixed device. Now you can approve this software device, and you can also modify it in some ways, restricted ways, in response to some of these concerns. The other thing that I think we really need to worry about, and there's been not enough work done in this area, and that is just what is the optimal way that humans and AI should interact? So this is some nice work on bias, not done at Stanford, on bias in mammography. So we have 3 different experience levels. We can say red is resident, blue is fellow, gray is attending. And when the AI gets the correct classification of the mammogram, everyone's fairly accurate. When the AI gets the incorrect answer, now you see it disproportionately affects the less experienced radiologist. And that it's something called automation bias. So the human is maybe listening to the AI more than he or she should. And we also have from other research that I'm not showing here, if you then take the AI away, the human, if you have a biased AI algorithm and you then take it away, the human will have learned some of the biases that the AI algorithm has. So we really need to think very carefully, and much more research is needed on exactly how humans and AI should interact to give the optimal human-machine system. The good news is, and I can say this has been true since I was studying AI back in the 80s, that human and machine are different forms of intelligence. And so they're likely to find different abnormalities. And so the combination of human and machine is better than either one alone. And that I think will continue to be true as long as we attend to these issues of human-machine interaction. Lastly, I often get asked, will AI replace radiologists? And happy to talk more about this in the questions if you like. But I think the answer is no. Radiologists who use AI will replace radiologists who don't. And I've spent a fair amount of time with arguing this point in this editorial, which you can look at if you're interested. And I do think that this really affects not just radiologists, but other physicians. Any physician who could be replaced by AI probably should, but I think there's so many aspects of our intelligence that can never be replaced. And I think that that's super important. So I hope I've given you a sense of how exciting it is in AI and radiology right now. I'm grateful to play a role in such a transformation of imaging and AI, and I hope I've given you a sense of the immense possibilities as well as some of the risks and challenges. So with that, I will stop, and then I will open it up for questions. Remember that you can put your questions in the Q&A box here, and I will be happy to address them. And I see there already is a question. And the first question is, does the de-identifier work for image and video files as well as text? And the answer is that we actually have 2 different de-identification algorithms. So there is a nice image de-identification algorithm that works on DICOM images that was developed originally by the Radiological Society of North America. It's open source, and so that's been adapted for use here at Stanford. And then there's the text algorithm, text de-identifier that we have that works on not just radiology reports, actually is state-of-the-art performance for medical record text as well. And so, yeah, we use both of those depending on the data type. And we'll have to continue to develop algorithms that de-identify medical record notes and that de-identify telemetry data and that de-identified structured data like lab results. So each data type will have its own kind of algorithm, and that I think is likely to continue. Okay, another good question is about legal and compliance barriers. Yeah, protecting data privacy. Are there to building large language models within a medical center like Stanford? It's a good question. So we think a lot about that. And I think that if we don't pay close attention to how we protect patient privacy, that's going to create a lack of trust, which I think would be appropriate. And so in order to maintain the trust that patients have in us, we need to attend to those issues. So we think very carefully about that. And HIPAA, which is the law that covers this, says that if you de-identify the data and the patient is consented, that you can then use that data for this form of research. There is some work that shows that you can sometimes extract some aspects of the training data from these large language models. If the data is de-identified, then you would never be able to find an identifiable patient, but you would, find associations between clinical conditions and those kinds of things. So I think we do a pretty good job of protecting patient data privacy. As the size of the data that we would release to the public gets larger, we have to worry more and more about those factors for sure. And the other, I guess, legal issue that we deal with all the time is like, well, if an algorithm makes a mistake, who's responsible for that and legally? And that's a question I get asked quite a bit. And it's important to remember that we've been using other forms of AI, like rule-based systems, for a long time with drug-drug interaction alerts or drug allergy alerts. And many of those are, in fact, rejected by human caregivers for good reason. And yet there really haven't been problems with that. And I would say the reason is because lay people and the public and the courts really want physicians to make the best decision based on all the information that we have. It doesn't matter what book you read, what course you took, what popped up in the medical record, or what AI said. You as a physician are responsible for making that best decision. And that's what, if you look at some of the kind of mock trials and some of the simulation studies, that's really what people are after. So I think that these are better tools than some of the older AI, but in some ways they're very similar in the way they fit into workflow. And I think the legal issues will be somewhat similar. Yes. Okay. The term bias has different connotations in the math stats world versus general audience. Yes. Any thoughts, suggestions? Yeah, that is a hard one. Yes, I agree with you. I think that so bias can be a good thing, right? We want the algorithm to be biased towards the right answer in a way, right? So it's going to pick out the aspects of the data that will lead it to the right answer. It's a matter of being fair is maybe another way to put it, that it's different than bias. So we want to make sure we have an algorithm that gets the right answer for all the different subgroups of patients, whether they're underrepresented or overrepresented in the training data. So we should be thinking about those issues up front and make sure we have the right training data so we have sufficient training data to generate an answer for everyone. I think that's important to consider up front. And when we do see bias, so for example, that example of a bone age and racial differences, the answer might not be to try to correct the algorithm. The answer might be to correct society. Like let's find a way in which we can have, if those differences are due to, say, nutrition status, maybe we should make sure that everyone is well nourished rather than try to fix an AI algorithm. So really a lot of complex questions there. Which of the FDA-approved 1,000 algorithms have been studied in randomized trials? Very, very few. That is something that we pay close attention to. I think for high-stakes algorithms, we should be doing those clinical trials. So, not all of those 1,000, in my view, need to have a prospective clinical trial. But in our center, we've done clinical trials of our coronary calcium algorithm. We've done clinical trials of our bone age algorithm. We're doing clinical trials of our pneumonia algorithm. So that's kind of our mindset. But on the other hand, we should recognize there are some algorithms, like an algorithm that might automatically measure the diameter of the aorta for aortic, aneurysm detection, that if we just, that's going to have a human in the loop, and it's a fairly simple thing, and it's saving us some time. If we just look at a certain set of those cases and compare to a human measurement, that's going to be, I think, more than sufficient for that. So we need to have an evaluation method that's appropriate for the kind of risk level of the algorithm itself. How is it decided what level of accuracy and de-identification was acceptable? Yeah. So when we have an algorithm, a de-identification algorithm, we have to think of two tiers of de-identification. So one tier is the level of de-identification that we use for within Stanford, within our firewall. We're not disclosing the data. We're just using it in the lab. And that's where we use the best available electronic de-identification. So we try to make algorithms that are as good as they possibly can be. And using these hide in plain sight methods are very good, so that even if a tiny amount slips through, it would not be detectable. And so that's kind of the level one. The next level of de-identification is if we want to release something publicly. We do release, as I said, we've released some of our data sets publicly. And when we do that, we have human review subsequent to the electronic review to make sure that there is 0 PHI detectable in those released data sets. And that's worked quite well. And I think that patients, if you survey patients, again, if they have consented, that they want us to use this data to help develop algorithms that are going to help future patients or perhaps themselves. I stated that AI has intelligence. What exactly did you mean by this? Yes, how do you define intelligence? Okay, so I left out, I have a part of my talk where we talk about what is AI versus machine learning and all of that. And so, I would say that artificial intelligence is when the computer does some things that we think of as being intelligent. But of course, that's a moving target. So when I was in grad school, AI used to be planning a driving route across a map of roads. Well, now that's like routine. It's in our phone. We don't think of that as AI at all. Now AI is driving the car, right? So there's kind of a moving target. So I wouldn't want to, I wouldn't want to necessarily say these systems have human intelligence. I think it's just different. There's a famous quote from Edgar Dijkstra who said, asking if machines are intelligent is about as insightful as asking, can submarines swim? So it's sort of it's a different thing that AI brings to the table, right? It's very spiky intelligence. It's very good at certain things. It's very bad at other things. And together with us, it's going to help us do some things that are that require some smarts. Let's see. Much is made of AI hallucination. It's great to see it falling fast. For a fair comparison, has anyone examined the same problem in humans? Oh, that's an interesting question. I don't know, but I mean, certainly I've known some humans that do occasionally make stuff up or say things that aren't correct. But I'm looking at this from a lens of a device that might be used in medical care. So we do have to have a higher standard for that. And I think it's very interesting. It will be very interesting to see how the FDA and other regulatory agencies manage this problem. I think what's likely to happen is that these foundation models will be a way for us to reduce the need for training data and increase the accuracy of some downstream model. So you have a foundation model that knows a lot about images, maybe abdomen CT, and then you'll build an algorithm on top of that that can find pancreatic cancer. And it will be much more accurate because it'll be based on that foundation of that massive training data set. And I think the FDA will care much more about the downstream model and the performance on that in detecting pancreatic cancer. And it might want to know something about the basic configuration of the foundation model, but the foundation model itself, I think it's going to be very difficult to get something like that through a regulatory approval, but we'll see. Is the infrastructure needed to support this AI within hospitals going to go up and well supported? Yeah. Well, our hospital at Stanford here has been very forward-looking with this. We have many of these language models are available now in a secure system. They're working on, chat with a patient's record, so you can ask questions to a language model about a particular patient's chart. All kinds of really fascinating applications. They're creating connections to the cloud where we can do these, execute these models where the compute power is present. So all of those things I think are happening. And I mean, it's not uniform, but I think that the healthcare industry in general is moving towards this infrastructure and the cloud more generally. Building medical foundation models. I'll ask this, it'll be probably my last question, then we'll have to go. Seems to be an initiative primarily led by academic medical centers. How do you see this trend benefiting community health systems? Yeah, that's a great one. I mean, it really gets to this sense of the need for diverse data sets, and often those more diverse data sets are in places where there are fewer resources. And I think it's a hard problem, and I think we will need to I'd love to see more programs that facilitate partnerships between kind of high resource, high knowledge institutions with respect to AI and lower resource, lower knowledge institutions, because I think that's the way that this technology is more likely to disseminate widely and to benefit patients across the board. With that, I think I will close here. Thank you for joining us for today's Grand Round session. Again, to claim CME credit, remember to text the code provided earlier to the number in the chat and you're seeing on the slide. And you can look for an email with more instructions after the session. You'll also find a link for a brief survey to give us feedback. Please take a few minutes to share your thoughts so we can improve future sessions. Thank you again for being with us today, and we look forward to seeing you at our next session next month. Thank you all.